Okay, this new unit is still organic chemistry, but we're now going to be looking at amino acids. So what we're going to do is we're going to look at what amino acids are, how they're made up, the common systematic names, zwitterions, and then how to identify unknown amino acids. So amino acids, they have an amino group and a carboxyl group. So an amino acid has a basic amino group and they have an acidic carboxyl group. And remember, an amino group is NH2 and a carboxyl group is COOH. So because they've got both basic and acidic properties, that makes them amphoteric. And that's because they've got both acidic and basic properties. So we've got this amino group here, which is basic, and we've got that carboxyl group, which is acidic. And together that makes them amphoteric. They're also chiral molecules. If you can't remember what a chiral molecule is, go back to some of the early videos on chiral molecules, just have another look. And they're chiral molecules because the carbon has 4 different groups attached. So let's have a look. We've got 1 different group, 2, 3, 4. So our carbon has 4 different groups attached. And that is what makes it chiral. So a solution of a single amino acid, the word that I always struggle with, entimer, will rotate plain polarized light. So again, that's a solution of a single amino acid, entimer will rotate plain polarized light. We have an exception, which is glycine. And I'm just going to pop our exception in here. Our exception is glycine, and glycine is an exception because its R group is just a hydrogen, so that wouldn't have 4 different groups attached because 2 of them would just be hydrogens. So that's basically what an amino acid is made up of. So naming amino acids. So amino acids have a common and a systematic name. And it would help if I'd not wrote systemic. I mean systematic name. So common names are things like glycine or valine, but each one also has a systematic name. So you should be given the common names if you need any of them in the exam, but you might be asked to work out their systematic names using the IUPAC naming system. I'm just going to go through that again. IUPAC naming system. And if you can't remember what the IUPAC naming system is, that is what we looked at the very beginning of organic chemistry. So when we first came across organic chemistry, this was our basic stuff that was in our introduction to organic chemistry. So if you're not sure of the IUPAC naming system, I suggest you go back and watch that intro to organic chemistry video that we did, and that's of the AS information. But we're going to have a go now at naming amino acid. So here's an example. You're asked to give the systematic name for the amino acid alanine. Its structure is shown on the right. So the very first thing you're going to do is find the longest carbon chain. So I'm going to pop that here as our number 1. We're going to find the longest carbon chain. And that includes the carboxylic acid group, and write down its name. So our longest chain here, we've got 1, 2, 3. So this is our longest carbon chain here. And the name of our longest carbon chain is propanone. So for alanine, as we've got here, the longest carbon chain containing the carboxylic acid group is 3 carbons long. So its name is based on propanoic acid. So let's just pop propanoic acid down for now. Propanoic acid. Next, we are going to number our carbons. So we're going to number the carbons. And they're the carbons of a straight chain. And we start with the carbon in the carboxylic acid group. So we'll start with this one here, and this will be number 1. That will be number 2. That will be number 3. Got that? Then, third step, we're going to write down the positions of any NH2 group. We need to find the positions of NH2 groups. And we need to show that they are NH2 groups with the word amino. So alanine has an NH2 group located on carbon 2. So that's our NH2 group. So that is our amino group. So to name that then, it's going to be, I'm going to get a different colour just so that we can see. So for naming this, it's on carbon 2. So it's going to be 2 amino propanoic acid. And that's all there is to it. However, depending on the amino acid, you need to make sure to include any other side chains or any other functional groups when you're naming that molecule. I've seen this example. There wasn't any others. If there is, make sure to include them. So that is an example of how to name amino acids using a systematic name. That can come up quite a lot. So we might go through some other exam questions later going through these. So Zwitter ions. Amino acids can also exist as Zwitter ions. And a Zwitter ion is a dipolar ion. And what we mean by that is it has both a positive and a negative charge in different parts of the molecule. Zwitter ions only exist near an amino acid's isoelectric point. And that is the pH where the overall charge on the amino acid is 0. And the isoelectric point is different for different amino acids. So here's our Zwitter ion in the middle. At the isoelectric point, both our carboxyl group and our amino group are likely to be ionized. And that is when it forms an ion called a Zwitter ion. Then, if we look at a low pH, in conditions that are more acidic than the isoelectric point, the carboxyl group is likely to gain a hydrogen. So this would happen here. Or at a high pH, in conditions more alkaline than the isoelectric point, the NH3 plus group is likely to lose a hydrogen. And that's at a high pH. And that's what we mean by a Zwitter ion. So let's say we've got an unknown amino acid. How do we identify it? So different amino acids have different R groups. And because they have different R groups, they will all have different solubilities in the same solvent. So what this means is that you can easily separate and identify all the different amino acids in a mixture using thin layer chromatography. And each amino acid will move up the thin layer chromatography plate at a different rate depending on how soluble it is in the solvent you've used. So what you do is you draw a pencil line near the bottom of a thin layer chromatography plate. And a thin layer chromatography plate is either a piece of plastic or glass covered with a thin layer of silica gel or alumina powder. And so we draw this pencil line at the bottom of near the bottom of the thin layer chromatography plate, and we put a concentrated spot of the mixture of amino acids on it. So you can see that right here. We've got the pencil line, and then we've got this concentrated spot right there. What we're then going to do is dip the bottom of the plate, but not the spot, so just before we get to the spot, into a solvent. And what will happen is as the solvent spreads up the plate, the different amino acids will move with it, but at different rates. So what will happen is they start to separate out. So we have our point of origin and we've got 1, 2, 3 different points. When the solvent has nearly reached the top, we take the plate out and mark the solvent front with pencil. And we then leave the plate to dry. And what we mean by solvent front is the distance moved by solvent, and we draw the pencil line on there so we know how far the solvent moved. Amino acids aren't naturally coloured, so you will need to make the spots visible before doing this. So you can do it in a couple of ways. You can either spray ninhydrin solution on the plate, and that turns the spots purple, or you can use a special plate that has fluorescent dye added to it. The dye glows when UV light shines on it. So where there are spots of chemical on the plate, they cover the fluorescent dye so the spots appear dark. And you can put the plate under a UV lamp and draw around the dark patches to show where the spots are. And then what we finally do is we work out the RF value of each amino acid using this formula given. So we use RF equals X over Y, which is our distance travelled by our spot divided by the distance travelled by the solvent. We measure the distance from the point of origin to the middle of the spot when we're working out our RF values. So the middle of this spot to the middle of our point of origin. You would then use a table of known amino acid RF values to identify the amino acids in the mixture. So you won't ever be expected to be able to know all the RF values off the top of your head. You have to just calculate the RF value and then you'll be given a table, usually in the exam, for you to then identify it with. What we're going to have a quick look at now is some exam questions based on amino acids. So valine is an amino acid with the molecular formula C5H11NO2. The longest carbon chain in valine is 4 carbons long, and you're asked to draw the displayed formula of valine and to label any chiral carbons with an asterisk. So the longest carbon chain is 4 carbons long. So we know it's going to have carboxyl group on there. So let's draw our carbons on first. So I'm going to have a carbon here, 2, and go 3, and then have my carboxyl carbon coming off here. So I've got my carboxyl group here. So it's C5, well, I've got 1, 2, 3, 4 at the minute, H11NO2. So it's going to be CH3 here, CH, and I'm going to have H3C there, H2N, our amino group, and then our hydrogen here. Have I got any chiral carbons? Yes, I have. This one is a chiral carbon. It's got 4 different groups attached to it. I'll get you 2 marks. And then you're asked to give a systematic name for valine. So we're 4 carbons long, attaching to the carboxyl group. So that would make the end part of it butanoic acid. Have we got any other groups coming off it? Yes, we've got a methyl group here. And obviously we need to number our carbons now. So we go carbon 1, carbon 2, carbon 3, carbon 4. So our methyl group's coming off our 3rd carbon. So we've got 3 methyl butanoic acid so far. Butanoic acid. And have we got an amino group? Yeah, that's coming off our 2nd carbon. So it will be 2 amino, 3 methyl butanoic acid. And that would get you your 1 mark, and that is your final answer for that. I've just broken it down into each step for you. So leucine is an amino acid with the systematic name 2-amino-4-methyl-pentanoic acid, and you're asked to draw the formula of leucine. So we can see how long the carbon chains are going to be because we've got pentanoic acid in here. So that means our longest carbon chain is going to be 5 carbons long. I'm going to draw that out first. 1, 2, 3, 4, and one of them will be our carboxyl group, 5. I'm going to number them. That'll be number 1, that'll be number 2, 3, 4, 5. So I've got 4 methyl, so I'm going to have a methyl group coming off my 4th carbon. And obviously another hydrogen coming off that one. Got nothing else coming off my 5th carbon, so that'll be CH3. Got nothing coming off my 3rd carbon, so that will just be CH2. This is going to be obviously OOH, H, and then 2 amino, so H2. So if I drew it without all the numbers on there, it would look like this. I get you 1 mark. So you're then asked to draw the displayed formula of the Zwitter ion formed by leucine when it is at its isoelectric point. So this part of leucine is not going to change. Again, your methyl group, not going to change. This is still going to stay the same. 3rd carbon, going to stay the same. This is where you're going to have those changes. It's all to do with your amino and your group and your carboxyl group. So your carboxyl group will be COO minus, and we've lost that hydrogen here. And your amino group would be have an extra hydrogen, so it'd be H3N plus. And then finally, draw the display formula of a species formed by leucine when it's dissolved in an alkaline solution. When it's dissolved in an alkaline solution, the ion side is towards the carboxyl group. So what you would have is this. Your amino group would look exactly normal. Oops, H2. Let me erase that. Let me try drawing that again. Again, methyl group not going to change. Your amino group is going to look like normal. You're just going to have COO negative there. So that was an overview on amino acids.